Okay?
Yeah.
Yeah, so there was no chain rule. There was no chain rule, dude. This is one chapter of House.
Oh.
You guys remember that guy?
Nah.
This is the one from last time. I was out for drinks with people and I showed them our suffering.
That gave them, gave us a lot of egg last time. So right now,
Quick question.
yeah.
Did you spend the whole weekend doing this?
What?
Did you spend the whole weekend doing this?
No. It's actually a lot nicer. There's the I don't know if you guys got the bonus, probably not. But in the bonus, I gave you a very nice way to solve this. And I'll probably show you that after, but I want to do the booklet first. So, first order of business, because this guy gave us a headache, we're gonna destroy his whole career. Let's actually start with the books example, or the books method. What did it tell us to do?
Probably like Doozie, like y prime equal y.
Yeah, it says v equals y prime, and then
Y
what?
prime equal y prime.
Was that the
No, it's v double plus v y equals.
It's what we wanted to change the variable in terms of y, right? So this was dy dt. And so what we think of as y double prime, well, that is going to be
dv over dy?
yeah,
Oh, wow.
dv dt, which was dv dy times dy dt, remember? Which was dv dy
Oh,
times e. That was the method that was suggested. And we went in and we plugged this in everywhere. So what did we end up with here?
dv dy times v.
Right, dv dy.
E squared. Equals 2v.
And we divided through by v. Huh? Yeah, because that makes it look Bernoulli.
But I don't think you have to do it that way.
Oh, we don't have to, but the book actually suggested it. It was a problem in the book. I believe it was 47 in section 2.9. And that was the suggested technique. Yeah, so this thing ended up Bernoulli with n equals -1. As long as n is not 0 or 1, it's Bernoulli. And so we did another change of variable, which was w equals v to the 1 minus n. So our dw dy is going to be 2v dv dy. And so we plug that guy in. And so what did we end up here? The dv dy was the 1 over 2v dw dy. And
There's a v that cancels.
then the v.
No. Oh, we got it.
Oh, I already divided through by the v. And the v is just, let's actually just put it there. And then we have this 2e to the minus y times e to the minus 1. And what we did was we multiplied everyone by 2v. So this became dw dy. This became 2v squared, but v squared is w, so that's just 2w. And this just becomes 4e to the minus y. So that became a first order linear differential equation. So we know that there's going to be an integrating factor. This is going to be e to the integral of the p. So in other words, it's going to be e to the 2y times w all prime equals 4e to the y. Right?
Yep.
And then what we did was we integrated. So we got e to the 2y w. Integral of this is just going to be the same guy plus a constant. Let's call that c1. That was 440. Okay, so now what? We solve for W. So our W is going to be
4e to the negative y plus c2.
okay, but our W was what?
B squared.
E squared. That was y prime squared. Okay. What did we do now? Did anyone actually go home and figure it out?
I did. Take the square root of both sides.
Take the square root of both sides. At this point,
You can do it.
we can do it. You believe in us?
The integral isn't that messy.
The integral for that isn't that messy?
It's not. Try it.
I want to try something first. So what I would do is I would multiply both sides by e to the 2y first. It's going to be the same kind of integral, but it's going to save us from a really ugly, an uglier substitution. So it's not going to be too bad. So if I multiply by e to the 2y. Now, here is the part that makes it a little bit easier to see. This guy here is actually just e to the y squared. Right? E to the 2y is the same as e to the y squared.
So it's really e to the y prime.
Oh! Right? Okay, now, noticing that, what's going to happen? Okay, so now noticing that, what is going to happen?
So they integrate the sides.
Well, you can't integrate both sides because of the square.
Oh, yeah, it's square. I thought that was a. You square root of both sides and you separate the variables.
Okay, so let's actually maybe do another substitution. Let's say, just to make it nicer for us, composition. This guy, this means that your v prime is going to be y prime e to the y. So right here I have v prime squared equals 4v plus c1. So my v prime is going to be the radical of 4v plus c1, include plus or minus. And so now separating the variables, I would get dv over this guy equals dt. Integrate both sides. Now, the integral doesn't look very scary in this form because just a u substitution in your du is going to be a constant, right? So that's going to become what?
For 1/4 times u, 2u, and...
So this is the guy to the negative a half. So we know we're going to add 1 to the power to make it positive a half, divide by the new power. And then our du is going to give us a quarter factor. So now we would have just 4v plus 1 equals t plus 2, right? So this is, of course, here a half. We multiply both sides by 2.
Square both sides?
We can actually square both sides. 4v plus 1.
Divide both sides by 4. That's all squared, so you have 4t.
I actually squared, but
14.
this is fine, but I want to square it in a nicer place because I want to get to the answer that looks like the book's answer. Just so, you know, just to embarrass this guy a little more, to show that we can get you in any form we want. Okay, so at this point, I squared both sides. So this will become 1/4 4v plus 4 equals t plus c2 all squared, because that part was in the answer in the book. Although, writing it as t squared plus 2, it wouldn't have mattered.
That's not a 4, it's c1. 4v plus c1.
C1. Okay? And so what do we have here? We have just the v plus some other constant, let's keep calling it c1. And so your v is going to be the t plus c2 all squared plus the c1, and your v was e to the y. You might remember that was the form that I told you the book had. That's the solution. That's the answer right there. Now, you could solve for y by just taking the ln, but the book wrote it like that. So now here's the thing.
So wait, how many substitutions do we do? 3. So 2 V's.
So yeah, for some reason last time, I don't know, I was just too tired. I forgot that that's the little thing I did to make it look nice. And the thoughts kind of flow easier after that. But here's something else. I just had a feeling that this was way too much work.
Right? I did too.
Yeah, exactly, right? So then I asked him, so yeah, this is the answer, but I feel like there's another way. And
Innovation.
here's an alternative. Which I kind of hinted to you in the bonus, because I gave you a very similar problem to this in the bonus. So, the other person I was discussing with said, you know what, it's kind of weird that there's a y prime squared there. Yeah.
I'm sorry, I just want to confirm, like, on the top right, on the second line, you have 1/4?
Yes, because I squared both sides, so the 1/2 here was squared to become a 4th.
Did the one, so when you...
I distributed,
So
the 4's cancel, that's just still a constant.
Oh, so you just absorbed that?
Yeah, so the quarter is absorbed in here.
Okay, thank you.
Yeah. So here's the thing. It's like, where would that y prime and y double prime, where would that y prime squared actually comes from? And here's where it came from. So this was a question on the bonus point on the quiz. What is actually, if I ask you the second derivative of e to the y?
E to the y.
No.
With respect to t.
E to the y, dy.
So that's going to be the derivative of the derivative, right?
Yeah.
What's the derivative of e to the y?
E to the y, dy, dt.
Right. Y prime e to the y, right? Now, if I want to find the derivative of that, what do I have to
Product
do?
rule. I mean,
I have to do the product rule. What's going to happen is I'm going to differentiate this part,
that's the
which
second.
gives me a y double prime, plus differentiate e to the y, I'm going to get another y prime e to the
And
y.
that's product rule.
I get a y prime squared e to the y. Notice what happens if I factor out the e to the y.
Wait, wouldn't it be y prime prime instead of y prime squared? Because it's dy dt and d. Oh wait, no.
It's multiplying. It's
Well-
product.
No, wouldn't d over dt times d over dt be the second derivative? Like if you
Yes,
multiply-
I took the derivative twice.
No, I mean for the product rule for when you take a derivative the third line, when you take the derivative of third line.
Yeah, differentiate this, that's y double prime, leave that alone,
Yeah, and then
plus leave this alone, differentiate that, and then I get another y prime from the derivative of this.
so
So that becomes squared,
all right.
because I have a y prime times a y prime. It's just y prime
Exactly.
squared.
Um,
Now if I factor out the e to the y,
all right, and get
I get that. So in other words, if I multiply both sides by e to the y, what is the left side? That's literally e to the y double prime. Integrate two times. This means that e to the y prime is just the integral of 2. And then e to the y is going to be t squared plus ct plus d.
Wow.
Which is the answer. If you expand the parentheses.
Let's do it.
That's a nice array. Let's move on.
Is there a name for that, or is it just a thing? It's just
Just notice, he noticed the pattern.
Cool.
Wait, who noticed it?
So that's just,
probably Bernoulli.
it's a Bernoulli. Like I had dinner with Bernoulli's ghost. And I was like, oh yeah, that's definitely it. No, it's not someone from here. It was someone I was discussing from another college. But he does work in PE, so it's just like, oh, by the way, there was this, we were hanging out, and I'm just like, there was this stupid little second-order differential equation that was giving me in my class a lot of trouble, and I got through the books way, but it feels like it's really hard. And I was like, oh, I think it's the second derivative over here. That's why you have the y prime squared. Of course, he would see it, like he does differential equations like all the time, so. Anyway, moving on. So there was, so we did it in two ways to show him he ate nothing. You ate nothing. Okay, so before we move on, some preliminaries. So I wanted to have a talk about some of the theory that's going on behind things like the existence and uniqueness theorem and all that stuff sort of thing. But I figured if I went into that spiel right now, we'd end class on a weird note where I wouldn't really have much to quiz you on, so I decided I'm going to continue with some technique stuff. And,
I don't know.
and then we'll talk about that later. So, let's start by looking at, do you know what the set of complex numbers are? So this is the set of all things that look like A plus IB, such that A, B are real numbers. And I, does anyone know what I is? It's the square root of -1 by definition, right? So someone didn't like the fact that they couldn't solve the quadratic x squared plus 1 equals 0, and they made up an answer to it. Now this is, in general, not a big deal, even though some people just start freaking out once they see a negative under a radical. But if you assume this has some meaning and you give it the name I, you actually get a way to solve any polynomial, and you'll have n solutions for an nth degree polynomial up to multiplicity. And I know that at City College you've had to avoid imaginary numbers in pretty much every math class up to this one. But yeah, suddenly you get here and we all expect you to know everything about them. So I want to talk, I'm not going to teach you everything about them, nowhere close, but I want to teach you enough so that you can understand some of the things I'll be talking about pretty soon. So note, if your I equals the square root of -1, what is your I squared? -1. If you cube it, what do you get?
Minus square root -1.
Well, minus I, right? And if you raise it to the fourth?
Plus 1. Plus 1.
-1.
Isn't it plus 1? I squared squared is just, I just I squared squared, and that's minus.
Yeah, because I'm taking this times I. So it's going to give me a -1, it's going to become a positive 1, right? And then, now what happens if I start multiplying by I to the 5th, it's going to loop back around, and the pattern starts over. Okay, so that's the first thing. You should know that this is has a cyclical pattern that is 4 steps deep. That's the first thing. So you would go from I to -1 to minus I to +1, then to I to -1 to minus I to +1. Every time you're multiplying by an I. Okay, now. You all remember, of course, that e to the x is the sum of what?
X to the n over n.
X to the n over n factorial. Now, here's a question. What is e to the I times x?
Minus
So-
one. Minus one.
What you can do here is e to the ix is going to be the sum
It's I sine theta plus cosine theta.
of this. That is going to be, pretty much when you start writing this out, you're going to get 1, then minus x squared over 2. Right, because when, 1, then I times x plus I times, let's just write out the positives. So this is when n is raised to the 0, n to the 1, n to the 2. So this is I squared x squared over 2 factorial, n to the cubed, I cubed, x cubed over 3 factorial. I just want to write out enough for you to see that there's going to be a pattern developing here. 4 factorial plus I to the 5th, x to the 5th, over 5 factorial, etc.
Yeah.
Now what's going to happen is these guys are going to change according to that rule that I gave you above. So that's just an I. When I see an I squared, that's going to become a negative, right? When I see an I cubed, that's just going to become a minus I. When I see an I to the 4th, that just becomes a plus 1. When I see an I to the 5th, that just goes back to I, etc. Now, you can start to group the things that have i's in them and group the things that don't. And so this is going to be equal to, let's throw all the guys that don't have i's, and let's throw all the guys that do have i's over here. Now what are the guys that are going to be over here? Well, 1 minus x squared over 2 factorial plus
X
x to the 4th over 4 factorial minus, you have eventually an x to the 6 over 6 factorial, etc. Okay. Now over here, the guys that have i's would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. You'll get a minus x to the 7th over 7 factorial if you follow the pattern. In other words, this guy is actually the sum of minus 1 to the n of x to the 2n over 2n factorial. And this guy is the sum, and goes from 0 to infinity of minus 1 to the n of x to the 2n plus 1 over 2n plus 1 factorial. And we also all remember what those guys are, right?
Cosine.
This is the cosine power series. This is the sine power series. Therefore, we obtain a very, very important equation. It is called Euler's equation.
One of them.
I have a question.
Yes?
I heard one way, but is it Euler or
Euler. There's no other way. Euler.
In Europe they say Euler.
Huh? It's Swiss. It's just they have a word pronunciation.
Yeah, it would have been like Euler.
So this leads to something called Euler's equation. E to the I times theta, it's usually called theta because we see that trig function show, is equal to cosine theta plus I times sine theta. Very important equation, you need to memorize this. It's called Euler's equation. Now, many people believe that this formula gives rise to the most beautiful equation in all of mathematics.
E to the pi I is equal sign. Square root, take 1.
If we are to plug in pi into this formula, if we set theta equals pi, what you obtain here is e to the I pi is going to be equal to cosine of pi plus I sine of pi. Now sine of pi is of course 0, cosine of pi is -1, And we obtain, therefore, that e to the I pi plus 1 equals 0. That is considered by many the most beautiful function in all of mathematics, because you have the number e, which you know e to the x is the most important function ever. You have pi, which is a number like e that all students below calculus revere. You have I, the imaginary unit. This guy allows us to solve every polynomial and get n solutions up to multiplicity. Then you have addition, you have the multiplicative identity and the additive identity all in one very short equation. It is considered quite aesthetic. That is, a lot of people, if you ask them, what's the most beautiful equation you've ever seen? A lot of people are going to tell you that. You know, kind of like how guys are like, the most beautiful girl I've ever seen was, 1969, I was in a bar. No, like, you ask a math person, what's the most beautiful? I remember the first thing I saw. We're going to talk about this. But that's an important equation. Now, unfortunately, we're just going to rush through here because we want to be able to use this to do something else. But before doing that, let's just do some examples. Compute. Not any tough examples, just some silly examples. So we already computed e to the I pi. Compute e to the I 2 pi, e to the I pi over 2, e to the I 3 pi over 2. And these guys are actually going to be important later when we get to chapter 4, believe it or not. Let's say also e to the I, let's say a plus ib. I put a sum in the power. Also, e to the ia plus ib times a variable t. Okay, so what is e to the I 2 pi?
1.
Right, you're going to have cosine of 2 pi plus I sine of 2 pi. That's 0. This is 1. So e to the I 2 pi is the number 1. E to the I pi over 2. It's cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0. Sine of pi over 2 is 1. So that gives you pi. E to the I 3 pi over 2. This is cosine of 3 pi over 2. Plus I sine of 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2
Minus 1.
is minus 1. And so that gives you minus I. So notice that...
IQ?
Huh? You could write IQ, but I don't. Oh, you mean from here? You can move the 3 out and use as IQ? Sure. But we can also put that in. So notice here, using Euler's identity, we can have a bunch of things happening. E to the I pi, I can get a minus 1. E to the I 2 pi, I can get a plus 1. And I can get plus and minus I. And notice, complex numbers are created by things like that. So in the future, if I wanted to create a complex number in a very convenient way, like an exponential, I can use Euler's identity to get it to happen. I can get i's in any location I want, whether plus or minus. And I can get the number 1 or minus 1 in any location I want, plus or minus. And then I can scale these to get up to other numbers. Now, what is this one?
E to the A, E to the IB.
Right, this is e to the a times e to the ib. So that is going to be e to the a times cosine of b plus I sine of b. Right?
And
Let me write that one down. By e to the a plus ib, and you'll see where this is going to come in handy very soon.
E to the AT.
Right, this is just e to the at times e to the ibt, and that's going to be e to the at times cosine of bt plus I sine bt. Right? And I can write this as e to the at cosine bt plus I e to the at sine bt. And
What's the purpose of distributing? Is there something?
Makes sense.
you mean the difference between this step and that step?
Yeah.
It's going to give us a nice form that I'm going to talk about later. Because I actually want to separate them. I know we're thinking of, right now you're thinking of this as like one equation, but there's going to become a point where I want to think of this as being something separate from that. So we like to separate them. Yeah, that's going to be important. So later I'm going to write something down and you might wonder, why is that? This is why. Right, okay.
That's a lot.
We'll talk a bit more about complex numbers as it comes up, but for now we're moving on.
You also use complex equations for
Oh yeah, yeah.
Yes.
But that's because like the complex plane with the unit circle. I never got why the
This
I
produces complex
the
numbers?
unit circle.
Huh?
This produces complex numbers?
It gives us another way to write complex numbers. You can say it that way. Pretty much any complex number I can write as a constant times e to the I theta. I'll talk about that later on too, chapter 4. We'll talk about that. For now, that's all we need for what I'm about to tell you. We are moving on to chapter 3, where we're going to deal with second order linear differential equations. Where the first topic. Let me just tell you what these are, and then I'll go down here. Okay, let's actually talk about a definition. What is a second order linear differential equation? So, definition. An equation of the form y double prime equals some function of t, y, and y prime is called a second order ODE. If f is linear in y and y prime, we call it a second order linear ODE. I will from now on write solely. Right? Second order linear differential equation. So to be more explicit, a solde is an ODE that can be written as, well, y double prime plus p of t y prime plus p of t y equals g of t. That is a second order linear differential equation. That means you solve for your y double prime, you get a linear function of the y's and the y prime on the other side. Right? Now, so that's one form. This form here is the standard form, so-called standard form. So if on the quiz I ask you, what's the standard form for a second order linear equation? You write that down. Right? So Q, your P, Q, and G are just functions of T. And this is something we'll get into, but this equation is guaranteed to have a unique solution on any interval where the p, q, and the g are continuous given two in the, initial values. But we'll get to that later in the theoretical point. Or sometimes you might have p, q, r, and g. Right, so sometimes you might be given a coefficient of the y double prime, you can divide through by that p of t to obtain that form. So I
use those specific function letters.
What about?
Those we just took. Does it matter if we use P of T, Q, T, R?
No, but if you use other letters than the p, q, and the g, it's fine. But this is the standard notation that your book uses.
Okay.
So just be aware that if you're reading from the textbook, there's room for confusion. We're gonna have a lot of variables all over the place eventually, so I probably just save myself the hassle and kind of write things how the book writes it, just to make reading easier. Okay. Now, if g of t or g of t is equal to 0, the equation is called homogeneous. Otherwise, it is non-homogeneous. Right, now this is going to be what homogeneous means from now on. For first order differential equations it meant something different, but for all higher order differential equations it just means the right side equals 0. It's called a homogeneous differential equation. So, i.e. boom, we have that, so y double prime plus p of t, y prime plus q of t, y equals 0. This is a homogeneous second order linear differential equation. Okay, now, we're going to spend a while on these. So let's get comfortable. It turns out that you need a homogeneous case to actually solve the case where it's not homogeneous. So we need to know how to deal with the fact when there's a 0 on one side as opposed to when there isn't. Because when there isn't a 0 on the other side, we are going to need to be able to know how to solve it with a 0 in addition to doing something else. Yep.
So, do we find a hazardous equation here? A hazardous equation?
A what?
A hazardous equation?
What do you mean?
Do we find that here? With homogeneous solution?
Well, it's a differential equation, so everything I tell you about differential equations still applies. You just, in order to solve this, you want to find the function y that makes that true. Right, so it's a differential equation. It has derivatives in it. To solve it means you want to find the function y without derivatives in it. And we begin with dot. Second order linear differential equations with constant coefficients. Things actually get a lot more complicated once the coefficients are not constant. So now, at this point, you might be a little bit discouraged because we started out with, oh, this is a second order differential equation. Oh, let's look at a second order linear. Oh, let's look at the guys with constant coefficients on 0. It's like we're weaning everything down to be the most simplest baby step cases. But it turns out that this case is actually super important. It has so many applications. Second order linear differential equations with constant coefficients that you would not believe. I'll talk about some of them. We'll do some of them, and we'll talk about some more as time goes on. So these have the form just AY double prime plus BY prime plus CY equals 0, where A, B, C are constants, and your A is non-zero. So now we're going to focus on this guy, which, yeah, I asked you about that. So,
I think it was like something on the first homework. Something
Yes.
similar to it. There was like a weird approach to it.
okay. Now, here's what we're going to jump into. How do we solve this?
Is it substitution?
And as is often the case in differential equations, we guess. What are we going to guess? Well, I want to think of a function that can reasonably behave in this way. Can I think of a function that if I start with that function and I take the derivative and its second derivative, they will all be like terms so that they can cancel each other out and get 0.
E to the x.
E to the x seems to be a very nice function to use. In fact, e to a constant times x to make it a little bit more general. Suppose the solution looks like e to the r t. This guy will have the potential that we need. When I take his derivative, he seems like himself. I'll always obtain a like term, right? Now, because I have a sum of 3 like terms, there's hope for some of them killing each other and getting 0. If I picked another function, like an ln of x, or ln of t, that wouldn't work, because I'd have an ln over here, and then a 1 over t over here, and a 1 over t. How do they all cancel out to get 0? Right? So e to the rt is a pretty good guess. And again, the theory that I'm going to be talking about later is going to tell us why it's okay to guess something, figure out how it works, and kind of prove after the fact that it's exactly the guy we wanted in the first place. So we'll kind of make a guess. This seems like a reasonable guess. Now, what's going to happen? If y equals e to the rt, then what is your y prime?
What do we do for
r e to the rt. What is y double prime? R squared e to the rt. Now, since y is a solution, it makes the ODE true. Which means I can go back to that guy and plug in this for the y double prime, plug in that for the y prime, plug in this for the y.
Yeah, the book actually did have us do this pretty early on in the book.
Oh,
Yeah.
awesome. Okay, good.
Yeah, it didn't make sense at all.
Yeah,
So, is it making sense now?
it is.
I mean, a month later, yeah.
Okay. Okay, good. So now what's happening, I'm going to plug it in here. So I'm going to have a r squared e to the rt plus b r e to the rt plus c e to the rt equals 0. Now I have this equation to solve. Notice that e to the rt is a common term. I can factor it out. Now I can immediately just divide both sides. This is never 0. So this means this guy must be 0.
Oh. Yeah.
How do we know e to the rt is never 0?
Because it is
An exponential
Oh,
function. It's asymptotic to 0, it never touches it. So it turns out, by this assumption, to solve this differential equation, I need to solve a quadratic equation. Remember on quiz 1 where I asked you about the quadratic formula? That's why. This is why I asked you about the quadratic formula. Do you remember how to deal with quadratics? You need to remember how to deal with quadratics. So now we have to solve a quadratic equation in order to find solutions.
This is the first web we're going.
So now AR squared plus BR plus C. Now what you want to notice about this is that there are three cases. One, you have two distinct solutions. Let's say R1 and R2, where R1 is not the same as R2. So you can have a quadratic that factors, you get two values, there are two different values, and you end up in this first case. Now in this case, here's how we're going to write the solution. So I know the solution looks like e to the RT, but I have two r's. What do I do with them? Well, I plug in one at a time and add them together in a linear combination. We're going to talk about why this works. In this case, y equals c1 to the r1 of t plus c2 to the r2 of t will give the general solution. So that's one case. There's another case. Sometimes your quadratic will be a perfect square. So it'll factor into like r minus something squared, and then you'll only get one answer. So sometimes you can have two, a repeated root, it's called. That is, you get one answer, called R. Okay. So this could be a complete square, and you just set the inside equals 0, you'll only get one value for R. And in this case, y equals c1 to the RT is going to be one solution. But for reasons I'll explain next time, we need two. How do you get the second one? It turns out that if you multiply this by a t, it gives you a valid second solution. Can you see that again? Multiply by a t.
So it's a different C1, like C1 turns into a different C2?
Yes. E to the RT is going to be one solution. E to the RT is the next solution.
It's a
But
derivative.
the constants are different.
We'll explain in 3.4. So I'll tell you why that ends up being the right second solution to pick. It is through, you figure that out through a process called reduction of order. It's going to be a method by which we turn the second order equation into a first order equation and solve for it, and it always ends up that we're going to end up multiplying that guy by t.
Didn't we do it already?
Yeah, we already did that. Miscellaneous.
Okay. Well, we're going to do it again a little bit more generally. Now, there's a third case. You plug into the quadratic formula because nothing factors, and you get a negative under the radical. You have complex roots. i.e., the r you solve for becomes a plus or minus ib. Right? That because there's a negative under the radical, it induces an I. And in this case, the general solution is given by c1 e to the at cosine dt plus c2 e to the at sine dt. What is that? Because the thing we showed you earlier. Once you plug in a complex number into the power of I, using Euler's formula, it's going to expand into something like that. There's going to be an I here, but I is a constant for all intents and purposes, so I absorb that into the C. Okay.
Would it be wrong if you rolled?
That's something.
That's it. That's all cases. You now know how to solve second order linear differential equations with constant coefficients.
So imaginary numbers are constants?
Imaginary numbers are constant, yes. That's always been the case.
But it's like imaginary.
Yeah, imaginary doesn't mean...
But it's constantly imaginary.
It's constantly imaginary. Okay, try these. Yes, I have a constant. So use what I show you to actually find the solution to these guys. And we'll see where you get with them next time. Let's say a this one I'm going to give you initial conditions. This means you have to find C1 and C2. -1 and -7 respectively.
But you always have to have two initial conditions in the system.
Yes, you have to have at least 2 initial conditions. And again, I'll tell you the theory of why that is the case. You need to have 2 linearly independent solutions with 2 constants. Solve this one, D. Now you'll need to use it's always going to be just those 3 cases that I mentioned. So just based on the quadratic that you get by trying to solve this with the guess, you'll know what to do in all the 3 situations.
Professor,
Yes.
we use this a lot in our vibration class to find out if a system is dense or underdense and critically dense. So in each 3 cases are vibrations? So each
That's an application.
Yeah.
So we'll actually talk about that later. That's a specific application which we will get into.
Okay.
It's not yet. Right now I just want you to know the
For
basics.
case 2, if you're only multiplying by p, how does the constant change? For case 2, for the second term.
Yeah, so this is what I was mentioning, that really we want to think of these as 2 separate things. Like this is like a y1, and that is a separate thing, y2. And the solution always has the form of a constant times y1 plus a constant times y2. So if you're in a situation where you could only find one solution, it turns out you can make up a second solution by multiplying by t.
Or you can
And there's a
divide by
specific reason why.
Did you divide by p if in the first solution there's one constant?
No, you just multiply by t to get the next one.
Why was it divided? Why doesn't it divide?
What's up, man? We go today.
That is, like I said, 3.4, I'm going to tell you why it's a t. It's not always a t in all cases. There are cases where it's not, but in this case, for constant coefficients, it's multiplied by a t. That's all it's going to